In this video, we're going to start looking at diluting solutions. So dilution. So diluting solutions is where we have a solution that's more concentrated and we want to dilute it, right? We want to make it less concentrated. So going from a higher concentration solution to a lower concentration solution. And the deal with diluting solutions is that we are not removing moles of solute, right? If we look at molarity, right? Molarity again is moles of solute per liter of solution. And if we wanted to make it less concentrated, right? We want our answer for our molarity to be a smaller number, right? If we're diluting it, we're going to something that's less concentrated. Mathematically, there's two options, right? If we want our answer to be smaller, I can make the number on the top smaller, right? I can have less moles. Or I can make the number on the bottom larger. That's also going to give me a smaller answer. When we're diluting a solution, so let's say I'm going from a 12 molar hydrochloric acid solution, right? So I have 12 moles of hydrochloric acid for every 1 liter of solution. And if we want to dilute that down to a 6 molar hydrochloric acid solution, we want to end up with 6 moles for every 1 liter of solution. However, we can't remove moles of HCl, right? These are itty bitty small little particles. And if you're doing this in the lab, you can't sit there with like some microscope and like microscopic tweezers and pull out molecules of HCl. We can't do that. It's just not physically possible to remove moles of our solute. So the number of moles of our solute that we have in our diluted and our undiluted solution is actually the same. What we do to achieve this new number is we actually add solvent, so our volume of our solution is going to get bigger. So what we actually do to achieve that number is you would take your 12 moles, since it's half the amount, we would want to have twice the volume, so I would divide it by 2 liters, and that's going to give me that 6 molar solution. That's how we're going to achieve this. So whenever we dilute a solution, and this is really important because we're going to derive an equation, and this is the basis for that equation, is that the number of moles in our solution is not changing. I have the same number of moles in my undiluted solution as I do in my diluted solution. The only thing that's changing is my volume, so thus my final answer changes. So when diluting a solution, the number of moles of solute does not change, right? It remains constant. What we end up doing is we add solvent, so the volume of solution changes, right? If the number on the bottom gets bigger, then when I divide that out, I have a less concentrated solution. So when diluting a solution, the number of moles of solute does not change. It's going to remain constant. And that is something that I ask you to know. So please pay attention to this. It's likely to show up as a multiple choice question at some point. So taking my molarity, so I'm going to put my capital M for molarity, and then I'm going to rewrite this a little bit weird. So I'm going to have moles, and then I'm going to put a V on the bottom for volume. Moles per liter, remember liter is a unit of volume, so I'm going to put that V down there. I'm going to rearrange this to solve for moles. right? I just multiply both sides by my volume, and I end up with that moles is equal to my molarity multiplied by my volume. And then I'm going to put some subscripts 1 on here. So that is my initial concentration and my initial volume. If we went back up and looked at my example here, my initial concentration is 12 molar, and in this example, my initial volume is 1 liter. I'm going to do the same thing for my diluted solution. So my number of moles is equal to its molarity times its volume, but I'm going to put a 2 down there for my new concentration and my new volume. So if we go back up, my new concentration is the 6 molar, and then my new volume. Since this mole is equal to this mole, right? My moles remain constant. M1V1 is equal to M2V2, right? If moles equals this, and then the exact same number equals this, that means that those two things are equal to each other. So my initial concentration times my initial volume is equal to my new concentration multiplied by my new volume. And this is an equation that we can use for diluting solutions. Again, this equation would not exist, however, if these moles were not constant, right? The only way we can make M1V1 equal to M2V2 is if those moles are equal to each other. So again, we're not removing moles of solute, we're adding volume, which then changes my concentration. Sometimes you may, if you've had this before, you might have seen I's for initial. Oops, that's supposed to be a V. You might have seen I's for initial instead of 1s. And then you might have seen F's for final instead of 2s. It's the same thing. So our original concentration times our original volume is equal to our new concentration times our new volume. And then also sometimes instead of an M, it'll actually do a C for concentration. Sometimes with the 1s and the 2s, sometimes with the I's and the F's. It's the same thing, it's just that this is concentration instead of volume. And the reason we would rewrite this is that not all units of concentration are molarity. So if we were doing like a percent solution, it could be like the percent of the first one times its volume is equal to the new percent times the new volume. So if you see it with a C, it's the same problem or the same equation, it's just we're being broader. Instead of saying it just has to be a molarity, it could be any concentration. An example for us. So what is the concentration of a solution prepared by diluting 250.00 milliliters of a 6.02 molar sodium chloride solution to a new volume of 1.04 liters. So problems like this, what I like to do whenever we have an actual equation, and you can actually do this problem using dimensional analysis versus using the equation. I actually learned to do it that way. I didn't actually realize that there was an equation for it until I started teaching, and our book had one, because I had just always done it using dimensional analysis versus memorizing an equation. And we can go through it that way also if you want, but I'm going to use the equation. This is how our text is going to do it and how most other instructors do it also. So when I have an equation, what I like to do is just make a list of what all of those are. I find that if I do this, I'm going to make less mistakes than if I take the numbers right from the question and put them into the problem. Sometimes you have unit conversions to do, and I'll just take care of that here and then plug everything in. If I just plug stuff in, often I'll put it in the wrong spot or I'll miss a unit conversion. So again, if you have an equation, I always like to make a list. It's just easier for me, and I would highly recommend doing it also, because like I said, it's really easy to make mistakes. This way, hopefully you'll catch them better. The other part that doesn't really matter is it doesn't matter if the ones are the original undiluted solution and the twos are the diluted solution, or vice versa. Since they're equal to each other, it doesn't matter. What matters is you keep the pairs together. So the part that you need to notice is that this number and this number go together. So we're diluting 250 milliliters of a 6.04 molar solution. If you want to call those ones or twos, it doesn't matter, but they have to be the same. So if you're going to make 250.00 milliliters M1, then you need to make 6.04 molar V1. If you want to make the 250.00 milliliters V2, then you need to make the 6.04 molar M2. I think I got the M's and the V's mixed up when I said it the first time, but hopefully I'm making sense. I'm sorry about that. But they both need to be ones or they both need to be twos. It doesn't matter which, as long as they're the same. I'm going to make them both ones, but again, it doesn't matter. It's just two multiplications on both sides of the equal sign. You can flip those around and it means the same thing. So my original concentration, 6.04 molar. My original volume, 250.00 milliliters. And again, make both of those the twos if you want. It doesn't matter. And then the new volume is 1.04 liters. And then we're solving for the new concentration. That's my unknown. So that's the one we don't know. And then this is where I'm going to check units. It doesn't really matter what the units are, as long as the similar quantities, like both volumes, have the same units. So these volumes, if I want them both to be milliliters or both to be liters, if I want them both, to convert them to cups, it really doesn't matter. They just have to be the same. So right now, one is liters, one is milliliters. I need to have them to be the same unit. It doesn't matter which one. I'm going to convert this one to liters, but you could totally convert the liters to milliliters if you want. And if you want to try it that way and see that you get the same answer as me, that would be cool. So remember that there's 1,000 milliliters in a liter. So I'm just moving that decimal place to the left 3 places. If you need to divide it out to be able to do it, by all means, just set it up using dimensional analysis. You're going to end up dividing by 1,000 or 10 to the third. And then don't lose sig figs when you guys do that. So I now have the same units for my volume. Molarity, I don't have a matching molarity, so I don't need to worry about units there. Whatever the one is what the other is going to come out to be. And now I'm going to plug them into my equation. So 6.04 molar multiplied by 0.25000 liters is equal to my unknown multiplied by 1.04 liters. And then when you do the math to solve for M2, our liters are going to cancel, right? We would divide both sides by 1.04, right? This is just straight up algebra, right? So these liters here would cancel. These whole quantities would cancel. So grabbing my calculator, and I get that my new concentration is 1.45 molar. Because I'm diluting it, my answer should come out smaller than 6.04. If your answer came out larger than 6.04, then go back and check your work because you goofed up somewhere, right? We know that we're diluting because my new volume is greater than my old volume, right? Remember, when we're diluting, we're adding solvent, so the volume of my solution is getting greater. Another example. So how many milliliters of a 12.0 molar hydrochloric acid solution do we need to prepare 750.00 milliliters of a 0.406 molar solution. So again, we're just using this equation. And I'm going to make a list just like I did before. So M1, V1, M2, V2. And just like before, it doesn't matter which are the ones and which are the twos, you just need to keep those pairs together. So kind of the second part, it says we're going to prepare 750 milliliters of a 0.406 molar solution. So those two go together, and then how many milliliters, so are unknown, and then the 12 molar, so those are going to go together. I'm going to make the 12 molar my M1, but again, feel free to make it M2. And if you do that, then your unknown is going to be V2, mine is V1. My new concentration, and then my new volume. And then units, I'm okay this time. I don't need to do anything. These are both molarity. This is in terms of milliliters, which means when I solve for my new volume, it's going to be in terms of milliliters. So plugging everything into the equation. And whenever I can reason through and kind of have an expectation for what my answer should be, or at least the range that it should be in, I always like to do that. It's really easy to set it up correctly and then just punch it into your calculator wrong or do the algebra wrong, something silly. So what I know, right, for sure, when I dilute a solution, my volume increases. So if I go back and look at my numbers here, this is my diluted solution, right? And I know that because 0.406 is smaller than 12 molar. So this is my diluted solution. This is my undiluted solution. I know that the volume of my diluted solution is bigger, so I know that the V1, the volume I'm solving for, needs to be smaller. So I'm going to expect when I hit enter on my calculator that my answer is going to be smaller than 750 milliliters. If my answer comes out to be larger, then I know I goofed up somewhere and I'm going to go back and check. I don't know that I'm right if it's smaller, right? I could have made a different mistake, but I'm not for sure wrong, right? If it comes out to be larger than 750, you are for sure wrong. So it's always good to reason through it a little bit. So just algebra, I'm going to take the 0.406, multiply it by the 750, and then divide by 12 molar, right? If we divide both sides by 12, then we get V1 by itself. And when I hit enter, my number is less than 750, which is good. Specifically, I got 25.4 milliliters. Right, from a unit standpoint, right, what I did is I divided both sides by 12 molar, so that went away. And then over here, 12 molar. So my molarities cancel, and I'm left with milliliters as my units. Significant digits. This is a mess now, when the 12 is 3. 0.406 is 3. And then 750.00 is actually 5. So I want 3 significant digits in my answer.